Today we're going to be having a look at something called Hess's Law. Now, in the previous videos, we have looked at how we can calculate enthalpy changes by doing experiments. So that's technically us working out the enthalpy change directly from an experiment. Now, that might not always be possible. Okay, we can't always do an experiment to find out the enthalpy change. That could be because a particular reaction might not be quick enough, so it might be quite a slow rate of reaction, and therefore it's not sensible to be doing that as an experiment in a lab. Another reason could be that the activation energy of that reaction is too high. It could also be that when we do the reaction between those two reactants, we might not actually make those products. Okay, we might actually make a different set of products, and therefore that equation that we're trying to work out the enthalpy change for doesn't apply. Okay, so there's many reasons why we can't work out enthalpy changes directly from an experiment, and that's where Hess's law comes in. What it does is it allows us to find out the enthalpy change indirectly. So first things first, we're going to have a look at what we actually mean by Hess's law. So Hess's law states if a reaction can take place by two routes and the starting and finishing conditions are the same for both those routes, then the total enthalpy change is the same for each route. Okay, so we can have two different routes to go from our reactants to our products, and as long as the conditions are the same at the beginning and at the end, then the enthalpy change is the same for both those routes. Let's have a think about what that actually means, how that applies to what we already know. So let's just do an enthalpy profile diagram. So I'm going to do a quick sketch of one. So enthalpy on this one, progressive reaction here. And I'm just going to pop reactants here, products over here. Okay. Now, usually we want to work out the enthalpy change, and as we know, the enthalpy change is always going from the reactants to the products. Okay, so this over here is our enthalpy change. But as we've said, we can't sometimes always work that out directly. Okay, so what we have to do is we have to take an indirect route, and it could be that we're given another piece of information. Okay, so I'm just gonna say that, let's say we're given this value here, so this is our indirect route, so we're going via this over here. Let's just assume that this is some form of intermediate. Okay, it's not the reactants, it's not the products, but we are going via this intermediate. So we're given this value here, so let's say that this value here is A, okay, and let's say we're also given this value over here, so let's call this value here B, okay, and our enthalpy change, I'm going to call that C. Now, each of these A, B, and C are routes, okay? So over here, we essentially want to work out the value of root C. So we want to know this, but we can't work that out. So we're going to take an indirect route. We're going to go via A and then go down B to work out our value of C. Okay, so essentially what I'm saying over here is that root A and B equals the value for root C. Okay, and if I were to put some numbers into that, you'll see how this works in a mathematical sense. So let's say that A is 100. So this value from here to here is worth 100 kilojoules per mole. And B over here is, because it's a downward facing arrow, let's say that that's minus 20. Okay, so if we're given the values of the indirect route, we can work the value of C out. Okay, and as we said, because we're going from the reactants to the products, so we're going to follow this journey over here. We're going to do 100 minus 20, so I'm just going to do that down here, 100 minus 20, and that's going to give us our value of C, and as we can see, that is just going to be 80 kilojoules per mole. Okay, so that's what we mean by using Hess's law to work out an indirect route to work out our enthalpy change. Okay, so as long as the conditions are the same in each of these stages, we can say that root A plus B equals root C. Okay, let's now apply this to some sort of exam question. So I am going to have to write out the exam question over here. There are two sorts of information they can give you. they can either give you the information of the enthalpy change of formation, or they can give you enthalpy change of combustion. So I'm going to do an example where they have given you the enthalpy change of formation, and you use that to work out whatever equation, whatever enthalpy change they've asked you to work out. Okay, so this one is enthalpy change of formation being given to you. So let's say they want us to work out the enthalpy change of reaction for this equation here. Okay, and the information, as I said, that they've given you is the enthalpy change of formation of these reactants and products here. Okay, so this information is what you would get in the exam. Okay, you'll be given this equation here, and with this information here, you are expected to work out the enthalpy change of reaction of this reaction here. So what they want you to do is work out the enthalpy change of going from these two reactants to these two products. Okay, and over here, as I said, they've given you the enthalpy change of formation of iron oxide and calcium oxide. Okay, so using this information, we are going to apply Hess's law and work out the enthalpy change of reaction for this here. So essentially what we're trying to work out is this root here. So we're trying to, this is our x, this is our unknown. Okay, right, given that they have provided us with enthalpy change of formation, if you remember, the definition of enthalpy change of formation is going from the elements to the compounds. Okay, so all this information here, so the enthalpy change of formation of iron oxide is saying that going from the elements to iron oxide, that's the enthalpy change. And the same thing for calcium oxide, going from its elements to calcium oxide, it's this enthalpy change here. Okay, so we're going to draw a Hess's cycle here. So what you need to do firstly is write out the equation at the top. And at the bottom of this cycle, because they have given us enthalpy change of formation, and formation always starts from the elements, I'm going to write elements at the bottom. Okay, you don't actually need to write the elements that make this. You won't be marked for that in the exam. Just write elements at the bottom. Okay, and we always, because we're doing enthalpy change of formation, go from the elements to the compounds. So my arrow is going to go from my elements to the compounds at the top. Okay, so to each of those, I'm going to draw an arrow going from my elements to the compounds. Okay, now another bit of information that, if you remember, is quite important here. The enthalpy change of formation of elements is always going to be 0. And that's why, so if we look over here, we've got calcium, which is an element, and we've got iron, which is an element. Okay, so they haven't given us the enthalpy change of formation of those because they're just 0. So technically, for elements, you don't actually need to draw the arrow for them because it's just going to be 0. So I'm going to rub them out just to make our Hess's cycle a little bit clearer. Okay, and now what I'm going to do is I'm going to put these values on my arrows, but make sure that it matches the molar ratios in the balanced equation. Okay, so we'll obviously check that it's the balanced equation first. So for this one, for the standard enthalpy change of formation of iron oxide, we've only got 1 mole of it here, okay? Because remember, these are just the formation of 1 mole of the compound. Over here, we've only got 1 mole of this, so that means this arrow here is worth minus 824. These are all kilojoules per mole, by the way, okay? So these values here are all kilojoules per mole. We're going to work out our answer in kilojoules per mole as well. Right, so we've done that arrow over there, and this arrow over here, so the one to make calcium oxide from its elements, forming 1 mole of calcium oxide is worth minus 635 kilojoules per mole, but we're making 3 moles here, so this arrow is actually worth 3 lots of minus 635 kilojoules per mole. Okay, so this is what we mean by an indirect route. Because we can't go directly from these reactants to those products there, we're going to go via the elements to get to the products. Okay, so this is one route. The other route is this one going from the elements, so going from the reactants to the elements, then to the products. Okay, so in order to work out this route here, we're going via this route here. Okay, So if we're going to go from our reactants to the elements, so this is our intermediate here, we need to go from our reactants to our elements. Okay, to do that we have to travel down this black arrow over here, but as you can see we're going in the opposite direction of the black arrow. Okay, so that means whatever value I have here, I have to change the sign of it. Okay, so if I'm going down this arrow, so in terms of what's going in my calculator, I'm going to write that down here in a different color pen. So I'm going to go from reactants to elements. So that's now going to be 824 because I'm going in the opposite direction of the arrow, so changing the sign. I'm now at my elements, and from my elements I want to go to my products. So I'm going to go up this arrow here. I'm going in the same direction of my arrow, so I'm going to keep the sign the same. So plus minus plus 3 lots of minus 635. So my calculator, when I plug this in, I'm going to get minus 1081 kilojoules per mole. So that root there is equal to minus 1081 kilojoules per mole. So that means this root over here is also worth minus 1081 kilojoules per mole. And that's my value of my X. That is the enthalpy change of reaction of this reaction here. Okay, so that's one example. Okay, so that's when they give us the enthalpy change of formation. Okay, the key thing to remember there is that you put elements at the bottom and all your arrows then, so your black arrows, the ones I've drawn here, all face upwards. So you always go from the elements to the compounds at the top, and any elements that you have here are just going to have an enthalpy change of formation of 0, and therefore you don't need to have arrows going up towards them. Let's now have a look if they give you another type of information. So this one, they gave you the enthalpy change of formation. Let's now have a look if they give you the enthalpy change of combustion. So this is the equation that they want you to work out the enthalpy change of reaction for. Okay, as you can see, this reaction here is actually the enthalpy change of formation of this compound here, which is called hexane. Okay, but the information they've given us, I'm just going to write this all down here. Okay, so this is the information they've given us. They've given us the enthalpy change of combustion of all of these over here. Okay, and they want us, using this information here, work out the enthalpy change of reaction, which is technically the enthalpy change of formation of hexane up here. Okay, so what we do is we look at the information they give us. They've given us combustion. So now the intermediate that we're going to go through is the combustion products of all of these. Okay, so if they give you formation, the intermediate you go via is the elements. If they give you combustion information, that means the intermediate you go through are the combustion products. And again, you don't actually need to say what the combustion products are. In this case, it will probably just be carbon dioxide and water, but you can just write combustion products here. Okay, so essentially, what we're going to look at is when you burn all of these, what's the enthalpy change? So now the key thing that's different from the one before is that all your arrows now need to point downwards. Okay, so we're going to burn all of these values here when we burn 1 mole of these. Okay, so all of these arrows now need to be facing downwards. Okay, let's now put these values in on the arrow. So if I look, actually no, let's just remind ourselves in terms of the roots. So we want to work out this root, okay, going from our reactants to our products. This is our X, this is our enthalpy change of formation of hexane, and that's what we need to work out. We can't go directly, so we're going to go via, so we're going to go down from our reactants via our combustion products and then go back up to our actual products. Okay, so that's the route that we're going to take, and that's going to equal this root here. Okay, right, I'm going to now put the values on the arrows. So if we burn 6 moles of carbon, So this is burning 1 mole of carbon. If we burn 6 of those, it's 6 times minus 394. This arrow over here is 7 moles of H2, so it's 7 lots of minus 286. And this one here is just 1 mole of hexane, so that's minus 4163. Okay. Now, in terms of what I'm going to plug into my calculator, again, I'm going to do that in a different colour pen. We have to go from both these reactants down to our combustion products, okay? As you can see, we're going in the same direction of the arrows, so the signs are going to stay the same, and all we're going to do is add up these two, okay? So if you have 2 arrows going in the same direction, you just add up those values there. So going downwards, we've got 6 lots of minus 394, and also over here, add 7 lots of minus 286. And that gets us to our combustion products. We then want to get to our actual products, so we're going to go in the opposite direction of this black arrow. Okay, and remember, if we're going the opposite direction, we change the sign, so rather than doing minus 4163, we're going to do plus 4163. If I now plug this in exactly how it is into my calculator, I get a value of minus 203 kilojoules per mole. Okay, so this route here is worth minus 203 kilojoules per mole, and based on Hess's law, this route from here to here also then equals minus 203 kilojoules per mole. So the enthalpy change of formation, which was this reaction over here, so the formation of hexane, equals minus 203 kilojoules per mole.